All right, let's take a look at the questions from our homework on page 569 from last night. There's 4 that we want to go over. Question 4, 5, 7, and 9, starting with number 4. A point in the Earth's atmosphere, at a point in the Earth's atmosphere, the electric field is 150 newtons per coulomb downwards. The gravitational field is 9.80 newtons per kilogram downward. We want to determine the electric force on a proton and the gravitational force on the proton at this point. Let's draw this. Okay, let's draw this to make it seem a little bit more straightforward here to us. Okay, at whatever point in the Earth's atmosphere, we have an electric field pointing downward. Its value is 150 newtons per coulomb. The gravitational field is 9.80 newtons per kilogram. We're used to 9.81, but okay, this happens to be a little bit above the surface of the Earth. The field strength is a little bit less. We want to determine the electric force. So forget about gravity right now. If you want to determine the electric force on this particle, then we got to use some kind of electric force or electric field equation here, right? What do we got? Well, generally when we see electric force, we probably think F is equal to KQ1 Q2 over R squared, Coulomb's law. Okay, the only problem is I don't have enough to do that, right? I don't know what R is. I don't know what the second charge is. I do know what the first charge is. It's a proton, right? But can't do that, right? So I'm probably going to be dealing with the electric field, finding the force with the electric field. In the end, I don't know whether this is a uniform or a non-uniform field, but I know that the proton is experiencing the field, and I know that the proton that experiences a field allows me to use the experiencer equation regardless of what kind of field it is, whether it's a uniform or a non-uniform field. So let's try this equation, E is equal to F over Q. Let's rearrange this to solve for F. And I get Q times E. 1.6 times 10 to the minus 19 times 150 newtons per coulomb. Make sense? You want to find gravitational force, so let's use the force equation that we've used since early on in Physics 20, which really comes down to, right, rearranging of the gravitational field equation, right? F is equal to m times g. Rearranged form of g is equal to F over m. So we use m times g. I don't know what we get for either one of those. You guys can calculate those values. Which one do you think is going to be bigger? Let's take a stab at this one. Which one do you think is going to be bigger? I don't even have the numbers in front of me right now, but I'm pretty sure I know which one's going to be bigger. Yep. The electric force, right? All other things being equal, the electric force is going to be bigger. Is it possible ever to have the gravitational force bigger? Sure. Sure, it's possible, but it's unusual. Generally, the only time that the gravitational force could be bigger is if the charge is essentially zero. So if something is neutral, then there is no electric field. And if there's no electric field, there's not going to be an electric force, right? But all other things being equal, if you have mass and you have charge, the electric force is almost always going to be bigger than the gravitational force. Number 5, a metal box is charged by touching it with a negatively charged rod. Compare the distribution of charge at the corners of the box with the faces of the box. Draw the electric field lines inside and surrounding the box. That's kind of funny. I didn't actually mean to assign this question, but that's okay. We can do it after we did yesterday's work, right? Because this has to do with charge distribution, right? We're talking about a box right here that has obviously 4 corners, and it's charged negatively. What are you going to see as far as the distribution of charges here? Where are the electrons going to tend to collect a little bit more in a higher concentration? Jacob? Probably the corners, because they're pointier, right? So you're going to get a higher concentration of electrons in the corners. Doesn't mean you're not going to get electrons everywhere else. I shouldn't say everywhere else. They're all going to go to the outer surface. The extra electrons are all going to go to the outer surface, but you're going to get a higher concentration of them at the corners than you will on the sides. Now, what about the electric field lines? We'll just draw the electric field lines kind of on one area, but it would look the same all the way around, right? The electric field lines here would look like this. What do you notice about the electric field lines at the corner versus along the sides of this metal box? Dylan? Yeah, they're tighter together. And what does that mean about the strength of the electric field? Yeah, it's a stronger electric field. And it makes sense that it's a stronger electric field, right? If you've got more charges there, then it's going to produce a stronger electric field at that point. Now, we haven't addressed inside here. Carrie, did you have a question? Yes, yes, they would. The concentration of electrons here would be the same as here and here and here, as long as the corners were all the same, right? If one corner was pointier than another corner, then all bets are off then. You're going to get a higher concentration at the pointier spot. But if it's a nice uniform thing, then yeah, it would be. Okay, what about the electric field inside? Electric field inside is going to look like this, right? And so on and so on and so on at all the other corners. If we added all of these electric field lines, these ones, along with the electric field lines all the way around, if we added them together vectorially, what would happen? This goes back to what we learned yesterday as well, right? If we added them together vectorially, what would happen? It would be zero. The field lines would end up canceling each other out, and the net electric field strength inside would be zero. What do we call that when that happens? Here's a nice little review of the stuff we did yesterday before I intended to review what we did yesterday. What do you call it when the field lines inside this metal conducting surface cancel each other out? What do you call it when there's zero electric field inside? Yep. Okay, the electrons are in static equilibrium, yes, but that static equilibrium allows the electric field lines to be kind of static as well, allows them to cancel out, produce a net electric field of zero. The whole scenario is what we call it's called a Faraday cage, right? Honestly, that term, you're probably not going to have to know that term. But in the end, you have to know what it is. You just might not have to know what it's called, okay? That's always nice to know what it's called too. You see something, with the video we watched yesterday, you watch something like that on TV and you hear them mention the word Faraday cage and you say, oh, hey, I know what that is. And sometimes it makes you feel all good inside because you know what they're talking about, right? Number 7, calculate the electric field intensity midway between two negative charges of 3.2 microcoulombs, 6.4 microcoulombs. They are negative charges. All right, let's draw this out here. Call this charge 1. We'll call this charge 2. Negative 3.2 times 10 to the minus 6 coulombs. Negative 6.4 times 10 to the minus 6 coulombs. The distance between the midpoint in each of the charges is 0.2 meters. And we want to find the field strength right there at point X. We know the field caused by charge 1 is to the left because it's toward the negative producer. The field caused by charge 2 is to the right, and it's toward the negative producer. How come I draw E2 a little bit longer? How did I know that the electric field caused by number 2 is bigger than the electric field caused by number 1? In fact, it should be twice as big. Hugh's nodding back there. How come, Hugh, the electric field number 2 is twice as big as field number 1? How do I know that without doing a calculation? Good. Charge is double, right? We find both of those fields. E1 is KQ1 over R squared. E2 is KQ2 over R squared. We calculate both of those fields, and we would find that E2 is twice as big as E1. Then we go to add them up. The net electric field, E1 plus E2. Just make sure that you make E1 a negative value and you make E2 a positive value. Is that all right? Who asked me for number 7? Is that okay? Do we need to go a little bit further with that, or are we good there? I think you would get pretty big numbers. Yeah, I think you would. I say that because the distance is yeah, I think you would. Does anybody else get big numbers? What'd you end up getting for the answer? $7,129 0, 0 for a final answer. 7.1 times 10 to the 5. Anybody else get that? Yeah? Okay. We've seen a lot of questions where the field strength is big, so don't lose sleep over that. I mean, I'm glad you're thinking about answers and are they realistic or not. Every once in a while when you do that, when you think about an answer and it kind of leads you astray every once in a while, right? But most times we start thinking about our answers. Are they reasonable? Most times that's going to help us as opposed to lead us astray. Problem is things like electric fields, we don't really have a frame of reference, right? We calculate a speed for something and it's like, oh wait, that doesn't make sense, right? We calculate an electric field. We don't have an experience of electric fields to know so much whether it's realistic or not. Yep. Well, we are in a sense subtracting them, but when we add them together, I always like to add because I'm finding a net, and net means the sum, right? But E1 is a negative value because it's to the left, plus a positive value. So in effect, you are subtracting them. I just think of it as adding, okay? Just assign a negative value to it. All right, last question, number 9. The magnitude and the direction of the net electric field at point P. Similar question, except this time we have our point outside those two charges. They have our diagram drawn for us this time. Let's circle this, because we got to convert that to coulombs, of course. I think we're going to end up with a pretty big one here, too. What was the last one, 10 to the 5? This one's going to be probably in the same range there. The field caused by number 1 is to the right. The field caused by number 2 is to the left. Now, which one's bigger? I don't really know this time, because although this charge is quite a bit bigger, which would produce a bigger field, this distance is also quite a bit bigger, which would produce a smaller electric field. Let's see here. We calculate both of those values. E1 is equal to KQ1 over R squared. Make sure you make R 0.45 meters though, right? We got to square 0.45, not 0.3. And then E2, we're going to find the same way. KQ2 over R squared. This one's a bit easier because our distance is simply 0.15. Get both of those values, add them up. But Nick, when we add them up, okay, you said a minute ago that why wouldn't we subtract them? Well, we kind of do, right? When we add them up, we make sure that we make the value of E1 positive and the value of E2 negative, which is mathematically the same thing as subtracting. Who asked me for number 9? Okay, is that good too? So the issue for both of them was probably your answer and how big it was, and did it make sense to you? Okay, so now you know. You get an answer on a test, it's a big value for electric field. It doesn't mean it's right, but it doesn't mean you have to stew over it for 20 minutes trying to think like, what have I done wrong? Okay, because we get big electric fields. Right? Okay, I want to try to do 2 quick questions here, 2 quick multiple choice questions. These questions are they go with the information that you just see on the board here. Questions number 47 and 48. Just take a look at 47 first. And let me just point out something about the information here. This information is old. In 2007, we switched curricula in Physics 30. Prior to 2007, you had to know about something called a transformer. Now we don't. Now that doesn't mean you couldn't get a question about a transformer like this, but it does mean that they'll give you a little bit more background if they did. They'd explain it a little bit more. They wouldn't expect you to already know what a transformer was. In this question, because it's pre-2007, they expect you to know something about a transformer already. So you read through this and you think, oh, that's a little bit tricky because I don't know enough about a transformer. That's expected. Okay, let me just tell you what you need to know real quickly here. There's what we call a primary side and what we call a secondary side. You're going to see in the question, here that we're looking for the strength of the electric field in the gap of the spark plugs. That's the secondary side, right? So we're going to be using data for the secondary side. If you're given data for the primary and the secondary, if you're looking for something on the secondary side, use the data for the secondary side. You would know all about that if you took Physics 30 10 years ago. As it stands right now, I have to explain a little bit of that to you because you haven't. All right, let's see what you can do with just question number 47 right now. Okay, let's take a look at question number 47 now. It says, what's the strength of the electric field induced in the gap of the spark plug? Let's take a look at our data again here. The spark plug is over here. I explained that was the secondary side of this transformer, this mysterious thing that now we don't really know a whole lot about post-2007. We do know that there is a voltage or a potential difference of 20,000 volts on the secondary side. And we also know that the electrical voltage to the spark plugs, or the gap in the spark plugs is 2.0 millimeters. We'll circle the millimeters because that's strange units here. In other words, we've got a potential difference over here of 20,000 volts. We've got a distance between the gap distance is 2.0 millimeters, or 2.0 times 10 to the negative 3 meters. And we want to find the electric field strength there. Now, in that gap, like let's say this is the gap here. In between that gap, like literally in between that gap, we've got a uniform electric field. Right now, I don't know whether it's going this way or the other way. That doesn't really matter. Now, outside of that, of course, we have those edge effects, but over a very, very tiny area, we'd still consider that to be parallel plates, right? Or something that approximates parallel plates. That means if we want to find the electric field strength in between that gap, we're allowed to use two equations. Remember the bottom portion of that Venn diagram. E is equal to F over Q, and E is equal to delta V over delta D. I think it's pretty obvious which one we're going to use this time. 20,000 volts divided by 0.002 meters. What is that? 1.0 times 10 to the 1, 2, 3, 4, 1, 2, 7? 1.0 times 10 to the 7, and that would be volts per meter, or you could say newtons per coulomb. Make sense? Here's a question for you. If the electron that jumped across this gap for some reason only jumped halfway across the gap, what would be the potential difference over which it jumped? It's jumped 20,000 volts here. It's gone from one side to the other. When it goes from here to here, it's gone 20,000 volts, a potential difference of 20,000 volts. Remember we defined potential difference as the difference in energy per coulomb between the two plates? It's the difference in energy per coulomb between the two plates is 20,000 volts. If it went halfway across, what would be the difference in energy per coulomb? No. Good guess though. Yep. 10,000 volts. It would be like a car saying, hey, what's the change in height as it goes all the way down the hill? 10 meters. Well, what's the change in height as it goes halfway down the hill? 5 meters. That make sense? If it went a quarter of the way across, then it would be, a quarter of the potential difference, 5,000 volts, or whatever the case may be. Okay, that's going to rear its head on Monday. The whole idea of the electron not necessarily going all the way across, but only going part way across the gap, or starting at one spot, and let's say it started right here, 3/4 of the way across. That means it's already gone through a potential difference of, what would it be, 15,000 volts, and it has yet to go through a potential difference of 5,000 volts. Was there a hand up there somewhere? Yep. No, you know what, I'm glad you asked that. And I should have just mentioned that, because what I just said could lead to confusion. I can see that. If I said you're only going halfway across, that doesn't change this. The potential difference across the gap is still 20,000 volts. Now, the potential difference over which the electron travels would be only 10,000 volts there. But when you're finding the electric field between the plates, it's not the experiencer that's the relevant thing. It's the producer. So what's the potential difference that the electron traveled across? I don't care. What's the potential difference between the plates? 20,000 volts. Make sense? So even if the electron only goes a tiny portion of the way across, that doesn't change the fact that these parallel plates produced an electric field of 1.0 times 10 to the 7. We wouldn't change delta V. We'd still make it 20,000, and delta D wouldn't be how far the electrons traveled, but rather it would simply be the distance between the plates, regardless of how far it's traveled. All right, real quickly, question number 48, so I can get a tiny little bit of new stuff covered here. The acceleration of the electrons in the gap is going to be, well, we just found the electric field, right? What was it, 1.0 times 10 to the 7? What other equation for electric field are we allowed to use when we have a uniform field? Okay, whenever you're looking for acceleration of physics 30, you use A is equal to F over M, right? Whenever you do. Whenever you want to find acceleration, but we got to find force. How are you going to find force? Because we don't have that right now, right? We got field, but not force. Remember the bottom part of that Venn diagram? There was the top part with two equations. There's the bottom part with two equations. We have the field found by this equation. We can find the force with this equation. So we can say F is equal to Q times E. Get the force, and then divide it by the mass of the electron. And whatever we get is whatever we get. Probably going to be a pretty big number. Again, I would think. Make sense? We won't bother solving that because we're trying to finish off a couple things here. I'm not going to spend very much time reviewing at all what we did yesterday, because in the end, the takeaway from it is a couple of main points. Number one, when you have excess electrons in a conductor, they want to reach a point of static equilibrium. What does that mean, static equilibrium? The forces are balanced. So these electrons, is there a question, guys? Sorry, go ahead. No. These ones here, you mean? No, you're not going to have to calculate anything there. Okay. The analysis, in fact, the analysis that I went through yesterday is likely more than you'll ever have to do. Okay, the takeaway from this, which is likely all you need to really have, a couple main things. I want you to have context, right? I don't want to teach you something that's just like, here it is, and then say, trust me. Okay, sometimes I have to do that, but when I can, I'd like to teach you why something is the case, and that's what I did yesterday. But the takeaway from it is a couple of things. Number one, when you have excess electrons, whether it's caused by lightning or whether it's caused by rubbing it against a dead rabbit or whatever the case may be, there's extra electrons on here. They want to reach a point of static equilibrium. In other words, they want, at some point, they will have the forces balanced, which means these electrons are going to stop moving around. They're going to be at rest. Now, when do they reach a point of static equilibrium? In every single scenario. Doesn't matter whether it's a uniform solid conducting sphere like this. It doesn't matter whether it's a hollow conducting sphere. It doesn't matter whether it's a conducting plate. It doesn't matter whether it's a nice smooth surface or a rough surface or a pointy surface or whatever. In the end, in every single case, the extra electrons will go to the outer surface. They'll always go to the outer surface. Got that? Okay, that's first thing. The electrons go to the outer surface. Second thing, if it's a nice uniform surface, like a solid conducting sphere or a hollow conducting sphere or a flat plate, they're going to be evenly distributed on the outer surface. But if it's a pointy thing, right, remember the irregular shaped thing, a pointy thing, then we get a situation where the charges aren't evenly distributed. In fact, we find that the charges end up being more concentrated at the point. Okay, and we saw that in one of the check and reflect questions we did, right, with the box. Okay, we saw that the electrons ended up being fairly uniform along the even sides, but at the corners where it was pointy, we found that the electrons ended up being more concentrated there. There ended up being more. Higher concentration of charge, higher electric field. Right, there you go. Okay, that's the takeaway from what we did yesterday. If I had just told you that yesterday, though, as opposed to gone through that analysis, then first of all, it probably wouldn't have made much sense to you. Second of all, you might have forgotten it. Okay, good news. We have 5 minutes. So let's do a little bit of stuff here in the next 5 minutes here. All right, take you back to gravity. Last year in Physics 20, we said in Physics 20 that the work done against gravity is equal to the change in gravitational potential energy. So in other words, this board marker is in my hand right now. If I want to change its gravitational potential energy by 100 joules, then I have to do 100 joules of work on it. Does that make sense? Change its potential energy by 100 joules, you got to do 100 joules of work on it. In gravity, the work done against gravity is equal to the change of potential energy. Well, same thing applies with electricity, except we wouldn't say work is equal to delta EP gravitational potential. We would say work is equal to delta EP electrical potential. For the first time, we're introducing electric potential energy. Okay, for the first time, there's going to be a possibility where you might mix up electric field with electric potential energy. Remember I said with the electric field, always put that arrow over? Okay, now we're starting to talk about electric energy, okay, which is going to start getting a little bit more confusing with the whole electric field thing. Work is equal to the change in electric potential energy. Now, one little definition for electric potential energy that's going to be a little bit foreign to you. It's really analogous to gravitational potential energy again, but we haven't defined gravitational potential energy this way before. We define gravitational potential energy in Physics 20 as the energy stored in an object due to its height above something, right? Remember that? The energy stored in an object due to its height. So the energy stored in this board marker right now is a certain value. Right now it's more because its height is more, right? Well, strictly speaking, we should have defined the gravitational potential energy is the energy stored in the system of the board marker and the Earth a certain distance apart. The reason we didn't define the potential energy that way in terms of the system of the board marker and the Earth is because the Earth is so heavy, it really has no potential to rise up to the board marker. It's the board marker that has all the potential. But strictly speaking, the potential energy is the energy that's stored in the system of the Earth and the board marker. But if the Earth doesn't really, for all intents and purposes, have any potential to rise up, let's just say it's the energy stored in the board marker. Does that make a little bit of sense? Well, let's look at the definition for electric potential energy. It's defined as the energy stored in the system of two charges a certain distance apart. That's a lot like the definition that I gave you for gravitational potential energy that we didn't really talk about in Physics 20. But this time, we have to include the system as part of the definition, because when we're talking about electric potential energy stored with two charges, it's not likely that one of them will be so big compared to the other. Here's a board marker that weighs, I don't know, 100 grams, if that. Here's the Earth that weighs 10 to the 24 kilograms. They're such a different mass, we don't really have to pay attention to the system. We can look at just an object. But the charges are usually much similar in magnitude that we do have to pay attention to both of them. The energy stored in the system of the charges a certain distance apart. Does that make sense? I have got for you right now the easiest question in Physics 30 that you will ever see. Okay, this is easier than anything you've done in Physics 20, in fact. Moving a small charge from one position in the electric field to another requires this much work. How much potential energy will be gained by the charge? What's our answer? 3.2 times 10 to the negative 19. This is a really easy question if you recognize that work is equal to change in energy. If you don't, you're not going to get this, right? Are you going to get a question this easy on a test? Not likely. Are you going to get a question that requires you to know that work is equal to change in energy? Maybe, maybe. So we still have to know this, but it's probably not going to be a standalone question. All right, don't forget, guys, Tuesday your assignment is due. I think if I remember, you're able to do all but one question on that right now. So get a good start on it this weekend, and then you can ask me questions on Monday if you have it.